Okay, so this video is going to be on black holes. So I promised you I'd show you the entire evolution of black holes. First I have to explain what they are before actually showing you how they form. So they have some features that a lot of people don't know about. The first one that I'll start with is gamma ray bursts. So once they've actually formed, once they have charge and an angular momentum, they're going to have some of these other properties, and that's going to actually make them unstable near their poles. That's going to cause them to eject matter at about 99% of the speed of light, usually within light cones within 3 degrees, in the form of gamma rays, which is the highest possible energy density or like classification, because it actually has a long span, but it's the highest classification of energy for that. The second one is the accretion disk, which most people know about. It kind of follows the galactic plane, when the supermassive black hole is at the center of a galaxy. It's just like a plane of matter that's following a regular circular orbital path, or called the geodesic, around the black hole. Then there's the ergosphere, which is where people stop kind of knowing about it. So there's this area around the black hole that looks kind of like two overlapping circles, like a Venn diagram. That's basically regions that are fairly close to the black hole. I don't actually have the equations written here, but where gravity starts to act weird, and your the geodesic, which is basically, geodesic is the word just to say like the path around. You go around another object. It could be on the surface or separated from the surface. They follow these polar functions, so like sine, cosine, and they have these kind of flowery shapes or whatever. But it just basically means that you don't have a radial escape velocity, meaning like if you tried to go this way out from the black hole, you're just gonna fall in, unless you're going like the speed of light. You're gonna have to follow a path where you'll have to accelerate in a way that will let you escape it. Then there's the photosphere, which is like this area that's, now you're getting really close to the black hole, where you just have, you're just going to get radiated by X-rays or gamma rays. And then there's the firewall. So the firewall comes from this idea that this physicist had when he was trying to use string theory to describe the surface of a black hole, called a fuzzball. So you can just imagine a bunch of strings, just one-dimensional strings describing the event horizon, the states on the event horizon, and all these crazy Hamiltonians describing the kinetic and potential energy of these strings or whatever. And that created this problem called the firewall, which basically said that information was going to get lost on the surface of the black hole because there's this area that's incredibly close to it, where you can think of it as, when I was talking about the phase split for the electric phase transition, this very high energy, where you lose all the gauge symmetries and physics stops making sense, and therefore you can't preserve information classically in the way that we would think about it. And so it's kind of basically like the hottest plasma you can think of. And I call it the Kugelblitz black hole generator. So I don't see it as really a problem, but that's because it is a real problem for classical physics, because most classical physics understandings of black hole have to do with ones that aren't charged and don't have angular momentum, and therefore they don't have as much matter falling into them, and they don't have the issues of the firewall. Alright, and then the last thing that everyone thinks of as the most famous part is the event horizon. The event horizon is basically the last place in our reference frame of space-time where you can assign a time to something happening, an event. So it's basically a Planck length from the event horizon. Anything that happens within this Planck length is essentially part of the event horizon, you could say, although the dotted line is the actual event horizon in this case, for example. Alright, so that has to do with the Schwarzschild radius, which is just a calculation that a physicist did showing that there's seems to be a limit on the radius of matter in general, or energy also. Could just be photons that don't have mass, but that would force it into a black hole. For neutron stars that occur naturally, if they are within 1.4 solar masses to 3 solar masses, they're probably going to be neutron stars, which is basically a state of a star where all the electrons and the protons have been converted to neutrons. So they're like very very dense, and they don't have charge. Although some of them, like our quasars, that means they do have charge and angular momentum. They're made out of strange quark-degenerate matter. And in that case, they actually do have charged cores, and some neutron stars have charged cores. I sent kind of like a diagram showing like the different makeup of the layers, like the outer and inner crust. You even have this concept called star quakes, where that's why quasars emit like incredibly powerful X-rays and certain frequencies and stuff. It has to do with that idea of star quakes. So let's go back a little bit. Photons are described by this letter gamma, solar masses, solar mass, entropy by S. This just means like Planck, so it could be a Planck time, Planck length, area, volume. Areas are like pixels, voxels are like volume. Let's see. So I just had, let's start with this basic intuition I had, which was that a point is like a conformal space that could be convergent or divergent, and it describes like a closed system of a Planck time. A length describes like within some reference frame, so you're now within some scale of the fractal continuum boundaries. You can think of as just many black holes inside other black holes. You're inside one of them, and therefore you have this reference frame for speed of light within this larger fractal continuum of VSLs, variable speed of light universes. And in your universe, this is the Planck length. This is the minimum amount of space you can transverse causally in terms of the quantum mechanical laws of your universe. And then I was thinking, well, usually they think of Planck areas as squares, just because it's natural to think of areas that way. You multiply some area by another one, and you're always going to get a square. That's just the easiest way to plot it. But if you actually wanted to minimize the area, the smallest shape you can make in terms of the area would be a triangle. And so I just pointed hyperbolic because I think of these areas as hyperbolic conformal spaces, but this is just an area. And then obviously that would give you like a pyramid, half of a tetrahedron, instead of the cube. And then this goes back to that other video where I was talking about the negative and positive direction of time for, you can think of them as black hole, white hole, extremal black hole, white hole, Feynman diagrams, and the symmetries that are produced on them. So here's like one Planck area. You can think of this as a graviton hitting the surface of an event horizon. It creates a pair production of a white hole and a black hole. You can think of the white hole as going down, so it goes down, and the black hole is going up in time. It's like converging versus diverging in time. I mean, that's kind of how I was thinking about it, but that one's still fuzzy because it's just a weird idea I had. All right, so now I was talking about the firewall as a Kugelblitz black hole generator. What I mean is this whole idea about Hilbert curves. When you're mapping a curve into an area, you can make it so that each point on that area is described by a point on the in the line, and therefore even something that's infinitesimal, like these Planck lines describing Planck lengths, can make up Planck areas, which can make up Planck volumes. So you can have an entire Planck volume out of just points that are mapping to each point within a Planck volume. As long as it iterates infinitely, you'll be able to describe it. So then I was thinking because of the Poincare conjecture that the simplest two-dimensional object is a sphere, so the simplest way to map onto a sphere would be to use the Fibonacci spiral method. And that's just the quickest way to pack these Planck times or points, which are conformal, which I think of as actual spheres, as actual black holes, on the surface of a black hole. So because past the firewall, pretty much you can't have anything except maximum Planck frequency twistors. The only things that they can really do is concentrate energy into a super small point, and that creates these Kugelblitz black holes, which are these points on the actual surface. So let's talk about Kugelblitz black holes, which are basically black holes made purely out of light, no matter, so just lasers. Let's say you want to make a black hole out of a cruise ship. It's 50 million kilograms. you would need it to concentrate it to an area 8,000 times smaller than a proton, and you would need about, let's see, the sun outputs around 3.85 times 10 to the 26 watts per second, and Earth gets about a billionth of that, and about 66% gets absorbed, but the other part of it gets reflected. So you need that output for a year to get enough energy that would feel enough gravitational force within the small area of 8,000 times smaller than a proton to make a Kugelblitz black hole. But at that energy, gravity really wouldn't work the same way, so all the gauge symmetries would collapse and wouldn't be able to resist. It would resist that collapse into a black hole, so you wouldn't actually get a black hole. So it's actually impossible for you to make a black hole out of lasers unless you're within a firewall, which nature does naturally. So let's see. I think that pretty much takes me into the whole idea that we had before about ADS space and three spheres and imaginary time and dream time and all that stuff. So first, obviously, there's this idea I had where twistors are hitting the event horizon and they're within this Planck space, and that Planck space is conformal to us, meaning like it's like those 50 millisecond bits of audio when you're listening to stuff. You can mix it up inside, doesn't really matter. So this one could hit before this one, or that one can hit before this one. Wouldn't make much of a difference. But there is a proper time. So there is a proper time based off of when they entered that event horizon space of the Planck space that tells you that there is a preference of least action for when these would basically emit these gravitons into the internal ADS space. So that's actually based off of the best way to pack the points on the surface of the sphere. So depending on in which imaginary instant, because this can be mixed up in any way, it's more efficient for there to be a point on that area, actually a graviton that's getting emitted into that point, then that's the one that's going to be working. So DNA, brains, computers, they all follow this Hilbert curve compactification basically of information, and they all follow these error correction code patterns. But I was thinking, well, there's a better way of doing it, combinatorial error correction code. So like this is a message, for example, bits of zeros and ones, and the rest could be error code correction. That's just a way for you to impact the code so that it can be recombinated and sent, and there's no error in it. But that code could be part of a larger code, and the rest could be part of the error code correction. Or another section could be part of the code, and this could be the error code correction, or this could be the code, and this could be the correction. And so because of that, you actually get a more complicated system that's able to basically be holding cohomologies. It's holding multiple patterns of these Fibonacci spiral methods at the same time and making them consistent. And so that's also the most efficient way to collect information from the universe, because if you think about a Penrose diagram where time is going this way and light goes in 45-degree angles, and this is space, this is universe, antimatter universe, white hole, black hole, so light's always going to be trending to the infinite future of a black hole, the event horizon or the inside of one or whatever. Because of that, what's the most efficient way? Actually, the universe would want the most efficient way to be sending light to the event horizons of all the black holes in the universe. So they might actually distribute themselves in terms of these Fibonacci spirals in the most efficient ways, aside from galaxies separating from other galaxies, just because in that way, the information would get to the black holes as efficiently as possible. All right, so we all know Penrose's conformal causal spaces is this idea of a hyperbolic space. You can think of M.C. Escher's art, where if you go towards the edge, it looks the same as the center, and the edge feels like it's at the center, and you can just keep going forever. That's really important because it's the only way to map an internal space of Hilbert curves from this problem of imaginary time, which has to do with the whole analogy I had for 50 millisecond bits of audio and how you can mess them up in any order from the inside. And it has to do with this problem called the adiabatic principle. So first, let me start off with this idea called gravitational time dilation, which essentially means that the rate of change in time when you're closer to the black hole compared to further away is slower. So you experience more time, essentially, until you get to the surface, and it's essentially an infinite amount of time. The adiabatic principle says you can essentially enter the black hole as long as it's not charged and there's not like a firewall, and you won't feel it. But from the outside, it'll look like you're just stuck in an infinite moment where time does not change at all. So that has to do with the idea of Susskind's complexity and the preservation of information on the surface of the black hole, essentially this Planck space. But the kind of where it breaks down is their idea of quantum circuits, which actually have to do with these twistors in imaginary time, but it's the same exact principle. Alright, so let's go back a little bit to Hawking radiation, singularity theorems, and the entropy equation by Hawking. So, Penrose and Hawking in the 60s essentially worked on this problem, which was taking the algebraic topology of the energy momentum tensors of Einstein's field equations to their limits, essentially saying certain stars of certain masses have to collapse into black holes. And in fact, that's saying something very deep and fundamental about the geometry of our universe. And then Hawking took it further later by talking about Hawking radiation, which is basically the idea that within this Planck space there's virtual particles that just form from the general energy density of this cosmological constant that this black hole is embedded in, this universe that it's embedded in, and these have positive and negative energy. Therefore, if one forms, this one can be absorbed and the other one could escape, virtually escape. It's still within this Planck space. And that would actually cause this black hole in proper time to decrease in area, because it would be losing mass. It would be absorbing negative mass. And so you have to kind of understand Hawking's entropy equations. So Planck's constant, first let's start with that. H has to do with joules per second, energy in relation to frequency of this is a photon. This is different from h bar, which has to do with the angular momentum. Basically, they just divide by 2 pi, because this photon's bound to some nucleus, a proton-neutron combination or whatever. So you have to understand that, because when you take this equation for entropy S of a black hole, it's related to the area. And h bar, this is for one that has nucleated photons that are orbiting a nucleus. This one's for when they're not. So you take this and you reduce it to a Planck frequency, so it's very, very small. And then you have to adjust for the speed of light, which is very, very large, and the area, and you have a huge entropy in the surface of the black hole. But then the area over time gets smaller and smaller and smaller. So it should evaporate away, essentially. But then I had this idea, which came from Penrose, which was that, well, eventually when the black holes explode and the universe is completely empty for a very, very long time, there's no reference frame of scale or whatever, so quantum mechanical fluctuations occur, and there's an entropy dip, and there's a Big Bang or whatever. It's an asymmetry again that forms just out of the natural fluctuations in terms of that energy density's creation of virtual particles. But there's a better idea that preserves information, I think, which is that black holes, they eventually become so small that they become internal to a causal conformal space of a Planck area or Planck volume. And because of that, in that conformal space, the reference VSL of that universe, within that conformal space, the black hole is now the largest boundary of that hyperbolic space, and therefore it immediately drops in entropy. It has a huge area compared to that gravitational constant, and that kind of solves the whole problem. And it could be that it's a bounce and that it does explode, and at the same time that it explodes, it does also stay conformal to this Planck space, just like the adiabatic principle, but for Planck spaces. And that could be true as well. So, trying to go fast because my phone was gonna die, but let's see what I missed. So, there's this idea of a three-sphere, which is essentially that there's these spheres everywhere and they're crossing over. And so in this sub-Planck space, I had this idea that there could be this virtual particle field. It feels like a virtual particle field, but it's not. It's really gravitons that are being created by twistors hitting the surface of the black hole within this imaginary time, past the firewall. And they're doing this pair production of black holes and white holes. And that pair production appears in this upper reference frame as just a lot of black holes that are overlapping in imaginary time. So we have this sense, we live in an imaginary instant, which is a single measure of this imaginary time, and so there is a proper order, and therefore only some of these are realized within the Schrodinger equation of our universe, and for that sake there is this order to the Fibonacci spirals and describing the orientation and locations of the black holes in our universe, and and so this three-sphere interpretation has to do with over a lot of time in this conformal space, the idea that over the average of the imaginary time of the existence of the black hole surrounding our universe, that all of these are realized, and so they're kind of simultaneous from this external reference frame. From the internal reference frame, they're not simultaneous at all. And so this has to do with the idea of the entanglement reference frame, the ER equals EPR idea of black holes being entangled being the same as particles being entangled. And so we actually have evidence of this three-sphere over imaginary time whenever we entangle particles. That's why the VSL idea becomes realized, and we're able to break the idea of locality. So on the bottom, you have all these white holes that are being formed by these pair productions. And these white holes from their reference frame are actually black holes, and we're actually in the direction of negative time. And to them, we look like the antimatter, so that's kind of the relationship to antimatter. I just made this grid again to explain how on the surface of the black hole, the twisters are creating these kinds of points of reference for this pair production. But really these are analogies for Wick transformations in the complex projective space within the black hole. You can basically mess with these combinatorially, same idea as the combinatorial error correction code, in order to make consistency of the cohomologies. You can essentially think of them as these complicated Mandelbrot-like structures on the surface of the black hole. Alright, so this internal area that has all these different black holes is called ADS space, essentially 5-dimensional space. I think of the 4D space inside one of these black holes as our universe, this 5D space of many 3-sphere black holes as the actual structure inside black holes, the 6-dimensional structure of this fuzzball as being the twister rays that are describing the subplanck space of the event horizon in imaginary time. And then I think of dream time as the sum of all possible imaginary times, which is just to say all the possible 3 spheres in the outside universe. And then after that, I don't really have a logical way of describing it anymore. But, let's see. Did I miss anything? Yeah. Don't think I missed anything. There's lots of other stuff on black holes I probably didn't talk about, but that's the general idea that I have of them so far. There's one more cool idea I'll share, which is that the Penrose process is an idea for how to extract energy from black holes, but it's incredibly unrealistic, but the efficiency is like much higher than nuclear energy, which is the most efficient way we have to extract energy right now. Alright, so I'll be done.